Today's topic is electrochemistry. Electrochemistry is a branch of physical chemistry which concerns itself with the interrelationship of the chemical phenomenon with electricity. It also deals with the study of the electrical properties of solutions of electrolytes, the effect electricity is going to have on chemical reactions, and also how electricity is produced during the course of chemical reactions. I am going to stick to certain aspects of electrochemistry today. We are going to see the difference between the electronic conductor and the electrolytic conductor. We are going to do some experiments to see the difference between an electrolyte and a non-electrolyte, a strong electrolyte and a weak electrolyte, the effect of dilution on in cases like acetic acid, which are normally very poorly conducting. So, we will do these experiments and then try to understand the basics of electrochemistry. Let me now start with a simple experiment using a household battery. I have taken a battery and I am going to use the bulb of this. Here is a setup of 3 cells. I have arranged them in series and we will now see what happens when electricity is passed through a metallic wire. This is a copper wire and we call it a metallic conductor. I am connecting these two wires, the negative and the positive terminals, as two different parts of this torch light. That is only to give it a continuity, and we have the electrical contact. Now, what I am now going to do is see what happens in a solution. In this case, I take a beaker and then have the same setup of the two wires and the battery is here. We will allow a small amount of electric current to pass through this and adjust these two wires suitably and take a solution of potassium iodide. Here I have got solid potassium iodide taken in a small container. I am going to add this potassium iodide here. This is solid potassium iodide. I shall now add water and make it a solution. You know that potassium iodide dissolves very easily, and here we have an aqueous solution, that is a solution of potassium iodide in water. Now, here is an aqueous solution. Now, we have some solid also left over. I will try to dissolve it. Potassium iodide is highly soluble in water, and we have here the aqueous solution or the solution of potassium iodide in water. Now, I place the two terminals, the copper terminals here, and I want you to note the changes very carefully. What is happening at the two different electrodes? You see that at one of the electrodes you see a yellowish color being developed, and the other electrode you see the bubbles of gases coming over. Observe it carefully. You have the color being developed at one electrode, and the other one you have the fine bubbles coming out. Now, this is the effect of electric current on chemical system. Now, what exactly has happened here? Now, potassium iodide has immediately ionized to potassium ion and iodide ion, and iodide, which is a negative ion, moves towards the positive electrode, anode, and then gets deposited as iodine, and this is the iodine color which is developed in this particular case. So, the yellowish color, and now it becomes deep yellow, afterwards it may become brown also, is because of iodine getting deposited at the positive electrode. At the negative electrode, we would normally expect potassium ions, but here instead of potassium, the gas coming out is hydrogen. The concept of ions was first developed by Svante Arrhenius. Arrhenius was a Swedish scientist who developed this theory of electrolytes and showed that any electrolyte, when in aqueous solution or in the fused state, in aqueous solution gives you positive ions and negative ions, and there is a dynamic equilibrium between the ionized and the unionized state. And on passage of electric current, the positive ions move toward the negative electrode, that is the cathode, and the negative ions move towards the positive electrode, that is the anode. That is exactly what has happened here. Iodide is a negative ion which moves towards a positive electrode, anode, and therefore, the charge on this iodide I minus is lost, it gets transformed into iodine, and you get this beautiful color. Now, what is the test for iodine? How do you know that this is iodine? I can do one small test and show you. I have starch solution with me now. I will remove this because this experiment is, a demonstration part is over, just to indicate that there has been a chemical reaction that has taken place on passage of electric current. Now, let me add some starch solution. I want you to observe very carefully what happens on adding starch. I will do this experiment now. See this beautiful deep blue color. This is the characteristic test to indicate the presence of iodine. Iodine with starch forms a beautiful deep blue colored complex. The one which was a pale yellow solution because of iodine has now got transformed into starch iodine complex, and this is the beautiful color. Now, that is about the difference between an electron, the conductivity due to ordinary wire which was giving you the glow here, and what exactly is happening when the same current is passing through an electrolyte. An electrolyte is a substance which allows electricity to pass through it, it conducts electricity, and not all substances are electrolytes. Some substances do not allow electric current to pass through. We will do one experiment and also see in this experiment what happens with dilution. Okay. I have a different experiment now. I want you to see this also carefully, because this is one of the very simple experiments which can be easily performed in a classroom setup. I have a bulb here, ordinary bulb, and I have arranged it in such a manner that there is a contact which I am directly connecting it to the mains, right. There is them connected to the mains here. Right now, the plug is switched off, and one other terminal of this wire is connected to a setup which is having some platinum electrode. You can have carbon electrode or any other electrode. For the sake of convenience, I have used a particular platinum electrode from one of the cells. Okay. Now, this is a loose contact, contact on one side with the platinum electrodes. I place this cell here, cell with a platinum electrode inside this. The beaker is right now empty. I am placing it here now, and I shall take acetic acid. Glacial acetic acid is the formula CH3COOH. It is a weak acid. I will add this glacial acetic acid some extent, and we can watch this experiment a bit more carefully. Switch on this and trying to place this electrode here inside this. Right now there is no glow in this bulb. Okay. I switched on this, there is electricity passing through this, and there is liquid here, and if there were some contact, we should have had some electricity passing through this bulb. Okay. Now, what I do is I try to dilute this. Okay. I am trying to add water to this setup. Now, immediately you see on adding water there was some glow, and now we will continue this addition of water again and see what happens. A faint glow here compared to absolutely no current passing, you have some current passing right now. Add some more water and see what happens. It is becoming more and more bright. What is the inference? That means acetic acid in its pure form, which we call as glacial acetic acid, is not conducting at all. It is not closing the circuit, it is not permitting the electricity to complete this circuit. But on dilution, when we dilute this acetic acid, you immediately see that with the increase in dilution, the glow becomes brighter and brighter. I can still add more, and I think it is sufficient evidence to show that increase in dilution increases the conductivity, electrical conductivity. This is one of the very simple and very fine experiments to show how this degree of ionization or degree of dissociation increases on dilution. It is a small setup, you can have carbon electrodes also and do it and see this particular phenomenon. I have switched off the light now, and now just for the sake of comparison, we will see what happens when we place this in some other substance. Okay. What we do now is we will wash this because it is already used for glacial acetic acid. I am washing this with water. Then I will keep this in another beaker, which is right now empty, and add some hydrochloric acid. The acid taken earlier was acetic acid, glacial acetic acid is organic acid. Now, I will take some hydrochloric acid, a little bit of it, and we will also make it a dilute solution and see what happens. You know, this hydrochloric acid is an inorganic acid, and from the properties of these acids, and in the topic you must have read this, hydrochloric acid is a strong acid, and from our experiment we have also noticed that acetic acid was a weak acid, and then as you go on diluting it, the strength of the acid increases, that is more and more hydrogen ions are formed. Now, we are now set for this experiment. I have taken hydrochloric acid in this, added some water, and see this, see the beautiful glow. You see the difference between the previous one and now. Hydrochloric acid gives you a beautiful glow as if it is directly connected to the bulb. Now, this is how we can differentiate between a strong acid and a weak acid, or a strong electrolyte in general and a weak electrolyte. Now, instead of taking this hydrochloric acid and comparing it with acetic acid, you can also take one salt and try to do that again. What I do is the same salt which I took earlier, like potassium iodide, and try to compare and do this experiment with the bulb and see what is going to happen. Compared to acetic acid, which was glowing but not so brightly, we see that in the case of potassium iodide aqueous solution or in the case of hydrochloric aqueous solution, the dissociation is almost complete. In other words, strong electrolytes, the strong acids dissociate almost completely, up to 99% and more, whereas a weak acid or a weak electrolyte, the dissociation is very less, but with the increase in dilution, the dissociation can slowly increase. Now, with these experiments, we can now differentiate between the two types of conductors. We move to the chart and see that conductors are of two types, electronic. The first characteristic is that the flow of current is due to the flow of electrons from a negative to the positive pole. It is a one side flow, whereas in the case of the electrolytic conductor, the flow of current is due to the ions, the movement of ions which flow in two directions. I have been emphasizing this particular point. Next, there is no change in the composition due to conduction. We have seen that nothing happened to the wire. The copper wire, which was allowing the electricity to pass through it, that is the flow of electrons, is still intact and it is the same copper wire. Whereas decomposition takes place and we saw that the solution has turned yellowish, it has become dark yellow because iodide got converted to iodine. So, there has been decomposition in the case of the electrolytic conduction. This is an important point. The conductance decreases with increase in temperature. We have not done this experiment, but experimental evidence shows that conductance decreases as the temperature increases in all these metallic or electronic conductors, whereas conduction increases with the increase in temperature. One of the reasons being that with the increase in temperature, the degree of dissociation is more, that the formation of ions is a lot more, and with due to that the migration of ions also is faster. Electrical conductivity is steady. That is what happens in wires, continuously there is a supply of flow of electrons and the circuit is complete. However, in the case of electrolytic conductors, electrical conductivity is not steady and it decreases continuously. It is seen that as the reaction, as the electricity flows, there is more and more formation of this iodide, that means the concentration of the iodide on the potassium and the respective positive ion here. In this case you got the bubbles. It is not that potassium is getting deposited, it is the hydrogen ion which is relatively easier to be evolved at the particular electrode, but all the same the concentration of iodide got decreased because of the conversion to iodine. So, electrical conductivity is not steady, it decreases continuously. One very advantageous observation is that electronic conductors follow Ohm's law and electrolytic conductors also follow Ohm's law, and because they follow Ohm's law, which has something to do with the relationship of resistance with the potential and current, and resistance with the length of the conductor and the area of cross section, we have a method of finding out or determining the electrical resistance or electrical conductance. What is resistance? Resistance is that particular property of any conductor to oppose the flow of current, whether it is electronic or electrolytic. So, this is the inherent property of all the conductors, be it electronic or electrolytic. One simple device to find out the electrical resistance is the setup which I have drawn here. This is a simple conductivity bridge. The principle used in this conductivity bridge is that of a Wheatstone's bridge. All you have to do is you have to have a Wheatstone's bridge, have a resistance box where you can have the adjustable resistance. We can have the resistance as desired in the experiment, and we have a long wire, a 1 meter wire usually, and here we have the conductivity cell. These are the two platinum electrodes, and we have the beaker containing a particular electrolyte. For example, if I were to find out the resistance of acetic acid, all I would do is take this acetic acid in a beaker here and introduce a conductivity cell. And here we have a wire which is connected through a headphone and a jockey which can slide along the wire. It has to be slowly moved, and this is a headphone. Normally you would have a galvanometer and you see the null deflection and you would do it. However, you have seen in this particular case it is finally connected to AC, alternate current source, because if you have the direct current source, you are not going, before you start determining the resistance, the substance will start dissociating and ionizing, and thereby you will never get a steady resistance. Alternating current is used in all the experiments pertaining to the conductivity measurements, so that we have the solution still intact. So, in order to adjust for this type of arrangement of alternate current, you have to have the headphone, and this headphone device is such that when you slide the jockey from one edge to another edge, there will be one particular point where you do not hear any sound. Continuously when you slide from one edge to other edge, there will be a sound, and you will have one point O when there is minimum sound or no sound. That corresponds to the null point. So, all you have to do is measure the length AO, measure length OB, and we know the resistance from the experiment because it is adjustable resistance, and this is the unknown. Applying the formula, resistance which is plugged out from this resistance box and the corresponding length AO divided by AO, resistance offered by the solution in the cell, that is resistance of the given unknown solution. As I said, if we had taken acetic acid, that means I am now measuring the resistance of acetic acid. Okay. So, that is the unknown here. OB length is experimentally determined. Out of the 4 quantities, resistance from the resistance box is known, AO length is known, OB length is known. From this, resistance of the solution in the experiment can be determined. Once resistance is determined, we have all the other quantities that follow. Reciprocal of resistance 1 by R is the conductivity. Conductivity is the measure of the ease with which electric current can pass through in a particular medium. Just like resistance is a property which opposes the flow of the electric current, conductivity shows you the E's. So, C, if you call C as the conductivity, is equal to 1 by R. Now, the units are also quite interesting. Resistance is expressed in ohms. In honor of the great scientist, on whose name the Ohm's law is based. So, resistance is expressed in ohms and conductance is measured in reciprocal ohms or mhos. In SI units, it is expressed in Siemens. Okay? So, conductance expressed in mhos, reciprocal ohms or Siemens. Let me conclude by recapitulating what we have studied in this lesson. Number 1, we saw the difference between electrolytic conductor and electrolytic conductor. We did some experiments with the electronic conductor as well as an electrolyte and saw the dissociation, the effect of dilution on acetic acid, and all these indicated that we have two types of conductors. We also studied about the determination of the resistance by the Wheatston's bridge and demonstrated two equipments regarding the measurement of conductance of an electrolyte.